we now manage to compute the probability of x as a simple sum over, for instance, the final state, and then probability of all observations and that final state, which is just alpha zn. And that is a lot, because as I said just before the break, we have a more than exponential number of paths that could have generated the observations. So if you remember the trellis diagram, I'm taking only 3 hidden states now. Let's assume that we have full connectivity. So the observations that we make could come from any of this tremendous number of paths that you can imagine. And naively, you would have to, if this is a given parameterization, naively, the way you would obtain this probability would be by saying that this is now a capital Z. We take, we marginalize out. Now these are all observations, and this is a sequence of hidden states, and we sum over all possible sequences of hidden states. So this is a tremendously expensive computation, and we replace it by merely summing here over the hidden states of a single variable multiplied with this alpha. And alpha, you have seen, you can obtain by a single forward recursion, so by a single pass. So essentially all it takes is a single pass through the data, and which allows you to replace this extremely expensive computation here. So this is the attractiveness of this forward recursion, and the backward recursion we will need later on for the actual learning of the parameters in the model. Now, it's just a graphical model, so why did we go about inventing these recursions in the first place when we already have message passing? And this was one of the triumphs of this field of graphical models, to show that these famous equations were just a special case of message passing, and we will verify that now. This is, by the way, closely following the exposition in the Bishop book, all of what we do today in HMMs, including his notation. So I'm drawing the factor graph of the hidden Markov model. Using the recipe that we saw earlier today. And again, these are the hidden variables. Oh, sorry, the observations. And the hidden variables up here. And then these factors. And I now shade these nodes here to indicate that, yes, these variables are really observed. And because they are really observed, we can simplify this factor graph and rewrite it as follows. Okay, so it becomes a simple chain. And we have everything that's missing has been integrated into these factors here. This is factor n. Okay, to allow for this equivalence, we note that this first factor h of z1, it integrates all of that, becomes this new factor here. So it is the probability of x1 given z1 times the prior probability of z1. And a factor number n, which depends on two hidden variables. Is given by, on one hand, the emission probability of xn given zn, and on the other hand, by the transition probability from zn minus 1 to zn. So all of that has been integrated into this factor here. And that is possible because the scope of this factor was a subset of the scope of that factor, so we can always subsume it under this bigger factor. Now, so we have this very simple, we have this extremely simple factor graph here, just a chain. So we can pass messages on that. So we have a message from hidden variable or hidden state n minus 1 to factor n. And if you remember, a variable that has only two edges will simply pass on the message it received from one side. So this is equivalent to the message from factor n minus 1 to variable cn minus 1. And secondly, we have the message from factor n to hidden variable n. So you could simply look up this algorithm that we had written down 3 hours ago. This is just what I'm applying now. So this is the native factor multiplied with all incoming messages, and there is just a single incoming message, namely okay, and well, this term is the one in the previous line, so I can summarize these two equations in a single one by writing sorry for these many indices. Okay, and you see the mu appears here and the mu appears there. So this is strongly reminiscent of, and in fact identical with, the forward recursion that we saw earlier. In fact, this is just alpha of Zn. So forward recursion is the same as message passing or belief propagation on a factor graph. And this relies on the first message being the same as in alpha recursion, and the update rule being the same. And if the first message is the same, if the update rules are the same, then the overall result is going to be the same. So bottom line, this forward-backward algorithm that had a life of its own before those graphical models people appeared, is just now subsumed as a very special case, just a special case of this general algorithm, message passing on factor graphs. So it is in that sense that graphical models are really a unifying model for many important methods. Okay, now sometimes you may be interested in finding which sequence of hidden states is most likely to have generated the observations. And this used to be known, or is still known in the field of hidden Markov models, as the Viterbi algorithm. And we will see that again, this is just a special case of a more general algorithm from graphical models, namely the max sum message passing. So not sum product, but this time max sum. So the single most likely sequence of states that might have given rise to the observations that we see is the maximizer of drawing these exaggerated z's to say that these are capital letters. These are really full sequences of hidden states. And for any graphical model, we can write this joint probability as a product over cliques and the factors depending on these cliques. And this maximization over the entire sequence could be rewritten as maximization over the first hidden state and the second hidden state and so on, up to the last hidden state. Now, that may remind you of something, namely, in the sum product algorithm, we had a similar expression where we had a summation over Z1, summation over Zn, so where we used to have summations, we now have these maximization operations. And now in the sum product algorithm, we push some of these summons in such that they had on the right-hand side only those terms that actually depended on the specific variable. And it turns out that we can do the same with these maximization operations. More in detail, the reason is that if we have a maximization only over Z1 of a factor over some clique 1. Sorry, this becomes illegible. This is clique 1. Yeah. And a factor depending on some clique 2. Then this is the same as, so we can pull this out just as we had pulled out terms in the summation. This is almost what we need. Almost, but not quite, because really we're interested in the argmax, and here we just have the max. And this is why we need an additional decoding step at the end. So overall, we can push this argmax operator in just as we did, the max operator. Just as we did with the summations before. Back in the days when we were looking at variable elimination. But here, because we're not interested in the maximum, but in which hidden state gave us the maximum, we additionally need to store which hidden state maximized one of these expressions. So similar to the sum product, if we maximize over a factor depending on x and y, and we only maximize over y, this will give us a new factor which only depends on x, but we need to store in addition the y star that actually gave us this maximum. And this stored value can then be used in the decoding step to find the best assignment. So we use this information in a decoding step at the very end. So after finding the maximum value of the entire expression, to find backwards one by one which states gave rise to this maximum value. So overall, we get out the argmax rather than the max. We get the best assignment rather than the highest probability. Okay, and this is so this decoding is performed by the Traceback Algorithm, which is described in the book by Koller and Friedman in chapter 13.1, if you want to look this up. And that is, of course, an embodiment of dynamic programming. Okay. So you can. So we now have nice tools already. We can compute the marginal probability of the observations under a given model. We can even find which sequence of hidden states gave rise to the observations, most likely. And for the driver intention example I gave originally, that would be a relevant example where we want to know for each time what is the most likely user intention, because the car can only react in a single way, so what should the car believe? But so far, we have always assumed that the structure or the parameters of the Bayesian network are known. And we have sort of glossed over this problem. This is actually why I used the stud farm example, because there, through Mendelian genetics, we knew all the conditional probability tables and so on. So that was all very nice. But in real life, we sometimes need to estimate the structure of the parameters of the Bayesian network. And that can be accomplished if we have some observations, if we have incomplete observations. That can be accomplished by means of the EM algorithm. So we can use expectation maximization to estimate the parameters, which sometimes amounts to, the whole structure of a graphical model, by maximizing the likelihood of the observations that are available. So we have an E step where we compute the expected complete log likelihood. So here we assume the parameters of the model to be known and estimate what are the hidden states that were probably visited. Here's this ominous sum over all possible sequences of hidden states. Okay, and there is the famous equation that we developed before, which happens to be a blackboard. Okay. And so we are now going to write all of that down explicitly. So we use the equation that's written here and multiply with this and sum over z. Again, making ample use of these indicator variables. And we then find the following. So I write the terms in the same order. So the equal sign refers to the last equation I wrote. And I change the order of summations. So I'm now summing over z. And then I have the probability of just z1 given all observations and these old parameters. And now we have that term that can just be copied. This term, we had already given it a name of its own. This is gamma of z1. And this summation over z together with this indicator variable assures that we are looking at all possible paths, but in this case just at their first state. Then for the next term, we have this summation over n. So next term, that one here. Summation over nj, k, and z. Out of all z's, we this time need to retain only zn minus 1 and zn. I warned you there would be a few more abbreviations. So this is psi of zn minus 1 and zn. And then there's the last term. So if you remember, somewhere deleted, there was the formula for how to compute these gammas. In terms of the alphas and betas. So gamma, when we derived what beta or how beta could be obtained recursively, we had noted that gamma of Zn could be obtained as alpha of Zn times beta of Zn divided by the probability of x. So each of these we know how to compute cheaply. The only unknown so far is this one here. So let's look at this psi. And using the same kind of manipulations that we did before, about 3 line of regroupings, which I spare you now, what you get is the following. A dependence, this can be expressed in terms of the alphas and betas as follows. So this is really not harder than the reformulations we've seen before. So we can also compute psi using simple recursive relations. So that was the E step, and in the M step, we now treat the gammas and the psi's. We keep them as fixed and now maximize this expected complete log likelihood with respect to the parameters which were pi and a and phi, using Lagrange multipliers to enforce the sum constraints. And if we do that, so maximize, this expression here, introducing these Lagrange multipliers, what you get is the following. So here we have estimated the probability of all observations and being in a particular state. And this thing is now, so where was gamma defined? Yeah. So this was the probability of being in a hidden state given all observations. And this is now the best guess that we got from our previous estimate using the old parameters. And this best guess is now normalized and used as prior. And the elements of the transition matrix are given by summing over all time points and averaging the probabilities that we previously computed that we think we had a transition between a hidden state Zn minus 1 and Zn. this here. Let me just check. Is psi of zn minus 1j and of zn k, which is used here. Okay, and the last parameter to be estimated that remains is those emission factors, and these can be easily expressed for multinomial observations and for Gaussian observations, and they have the form that you would perhaps expect if you know if you already know mixtures of Gaussians. So I'm only writing them down now for Gaussian observations. So it means the observation that you would expect when being in hidden state number k has a normal distribution with some mean mu. It's not a message now, but it's the mean of the Gaussian, and some covariance function. And we now get the equations for update of these parameters. So the mean for hidden state number k can be computed from the gammas. Where gamma of z and k is this quantity here. So the expected value of gamma. So if you squint, this is just a weighted mean of your observations, where each observation was weighted with the probability that you think it generated from hidden state number k. That makes sense, I think. And the same weighting factors can also be used in the computation of this covariance matrix here. Okay, and that's it. So now we have all that we need to learn the parameters in our HMM. You still need some kind of initialization, which we did not discuss. So if you have some prior knowledge on which hidden state might be responsible for a given observation, then you could use that knowledge to initialize your, let's call them the clustering parameters here. And similarly, for the transition matrix, If you have a good guess, then you should of course use that to initialize your transition matrix. If you have no good guess, and if you cannot rule out that there may be transitions between two possible states, then it's best to use at least a small non-zero value for each possible transition. Because if you set a transition to totally zero at the start, so if you forbid a transition in your initial matrix A that you use, then you will see that in the E step, your size will tell you that this transition is not possible, and hence in the M step you can never introduce that transition because it uses those size. So the zeros that you introduce in your transition matrix will always persist. And if you're not sure that a transition is totally forbidden, then use at least some small value for initialization. So we have met a very useful model. As I said, it's used in bioinformatics, in speech recognition. It's used in all kinds of control systems. And you now have all the ingredients to make it work. I did not discuss the normalization of those messages because it turns out that you compute small values with even, or you multiply small values with even smaller values. So to prevent problems with underflow, you need to work in the log domain or use normalizing factors. Yeah, we don't have time for the Kalman filter. I've just heard that word. The Kalman filter uses just the same graphical model. So in the Kalman filter, you have the identical graphical model, with the difference being that you assume both the observations and the hidden states to follow a Gaussian distribution. So in the hidden Markov model, you have a discrete space for your hidden states, or you have discrete hidden states. In the Kalman filter, you have continuous hidden states. But other than that, the ideas that we have used here carry over. These concepts of marginalizing out. The principal difference is that the marginalizing out now happens not with a summation, but with an integration. And what you effectively get is an integral over some Gaussian with another Gaussian. And it turns out that that is, again, normally distributed. So you start with a normal prior, you have a normal observation, so this one is going to be normal. And then you can use Bayes' theorem on normal distribution, so that one will be a normal, and so on. So you keep propagating a normal distribution, and that is the preeminent method for tracking, which, however, has, since it's just a linear system, has, of course, a number of limitations. So it can only deal with, at least in the original implementation, can only deal with a single particle. The proper generalization to multiple objects to be tracked is totally unaffordable. So that's multiple hypothesis tracking. And then, well, you don't really believe in such linear systems. So tracking was born in the military industry and in the space faring industry. And in the military industry, if you track an enemy plane and it's going straight for a mountain, then it's not very likely to predict that it will continue on that course. So you need more nonlinear information to really model complex behavior. And hence there have been a number of generalizations to the Kalman filter, such as the particle filter, which I have no time to discuss. I want to give you a few more comments regarding the exam, which we will do without the camera, perhaps.